Hello, my name is Markus Lohrey, and this is joint work with Loro Bartholdi, Michael Figelius, and Armin Weiss. This talk is about the computational complexity of the word problem and also the circuit value problem for groups. So let me start with the group theoretic background. In this talk, I will mainly speak about infinite but finitely generated groups. So that a group G is finitely generated, I use the abbreviation FG, means that there is a finite subset sigma of the group, such that every element of the group can be written as a product of elements from the set sigma. In other words, every element of the group G can be represented by a word over the elements from sigma. In such a word, you may use a generator, so an element from sigma several times. So the elements of sigma are also called the generators of the group. There is a technical assumption, namely we assume that the group identity belongs to sigma, and if A belongs to sigma, also the inverse of A belongs to sigma. Now the first computational problem I will speak about is the word problem for a group G. The input for the word problem is a word W over the generating set sigma, and the question is whether the word W evaluates to the group identity in G, or whether W represents the group identity. As it is formalized here, the word problem depends on the generating set sigma, but it's easy to see that the computational complexity, also the decidability of the word problem, does not really depend on the generating set sigma. So therefore one can speak of just of the word problem for the group G. The word problem is quite old. It goes back to work from Max Dehn from 1910, and Dehn was interested in topological problems, and thereby he proved that the word problem is decidable for fundamental groups of two-dimensional surfaces. Actually, also Turing was interested in the word problem, so in the 1930s he tried to prove that there are finitely presented groups with an undecidable word problem, where a group is called finitely presented if it can be defined by finitely many identities. But Turing did not succeed. Only in the 1950s, Novikov and independently Boone could show that there exists finitely presented group with an undecidable word problem. Here, I'm mainly interested in groups with decidable word problem and in their computational complexity. So let me give some nice examples. So first of all, it's easy to see that for every finite group, the word problem can be solved in polynomial time. And actually the complexity is in NC1, so you can solve it by bounded fan-in Boolean circuits of logarithmic depth. When I speak about NC1 in this talk, I always refer to the ALOGTIME uniform variant of NC1. For finitely generated linear groups, you can solve the word problem still in deterministic log space, and this is a result which goes back to Lipton and Salkstein. Now there are many other results in group theory, for instance for hyperbolic groups, which are very important in geometric group theory. You can solve the word problem in linear time. For so-called automatic groups, you can solve the word problem in quadratic time. And for one-relator groups, which are groups that are defined by a single defining identity, you can solve the word problem in primitive recursive time. Nothing better is known in this case, and there are also no lower bounds, and actually the exact complexity of the word problem for one-relator groups is one of the big mysteries in group theory. Now let me come back to finite groups. As I mentioned, the word problem for every finite group belongs to the circuit complexity class NC1. And actually there's a very nice dichotomy in this case, which was proved by Barrington in '86. Namely, if G is a finite non-solvable group, then the word problem for G is NC1 complete. On the other hand, if G is solvable, then the word problem for G belongs to the circuit class ACC, which is a subset of TC0, which is, by many people believe that TC0 is a proper subset of NC1. The main trick for Barrington's proof is the use of commutators in non-solvable finite groups. So let me briefly sketch the argument. If you have two elements A, B from your group, which are non-trivial, so not the identity, then the commutator of A and B is A minus 1, B minus 1, AB. And let's assume that this commutator is non-trivial, which means that A and B do not commute. Then you can implement a logical AND gate in the following. So if X is either 1 or A, and Y, the group element Y, is either the group identity 1 or B, then the commutator of X and Y is non-trivial if and only if X is not equal, is non-trivial, and at the same time Y is non-trivial. So in this sense, you get a logical AND gate if you identify the group identity with the truth value false, and any non-trivial element in the group is identified with the truth value true. Now, in order to simulate Boolean circuits, which is necessary in order to prove NC1 hardness of the word problem, you need non-trivial nested commutators of any depth. And they, in fact, exist in finite non-solvable groups. Now you might ask, what about the word problem in an infinite but finitely generated non-solvable group? Is it also NC1 hard? And one might think that this is the case because, well, somehow infinite non-solvable group appear more difficult than finite non-solvable groups. But actually, we don't know the answer to this question. And the first goal or the first achievement of our work was the definition of a quite large class of infinite, finitely generated non-solvable groups where we can still prove NC1 hardness of the word problems. And we call these groups uniformly, strongly, efficiently non-solvable, or briefly, uniformly sense. So the definition of these uniformly sense groups is a bit technical, but let me go through the details. So let's take a finitely generated group G and fix a generating set sigma for G. Then G is called uniformly sense if for every number D there is a perfect binary tree T sub D of height D. So it's a binary tree where every path from the root to a leaf has exactly D edges. And this tree has the following properties. So first of all, every node of the tree is labeled with a group element, which is non-trivial. I call it G sub V. Moreover, if V0 is the left child of V and V1 is the right child of V, then G sub V is the commutator of G sub V0 and G sub V1. So that's basically what I mean by a tree of nested commutators here. And then we need some, effectiveness conditions, namely, first of all, every group element G sub V of our tree can be represented by a word, I call it W sub V, of exponential length, exponential in D. And finally, if I give you a leaf of the tree T sub D, so let's call it V the leaf, and a binary encoded position I in the corresponding word W sub V, which represents the group element sitting at node V, and a generator A from sigma, one can decide in linear time whether the ith letter of W sub V of the word is A. So that's the definition of uniformly sense groups. It's a bit technical, but that's how it goes. So first of all, it's easy to see that every uniformly sense group is really non-solvable. Otherwise, the notion uniformly, strongly, efficiently non-solvable wouldn't make much sense. But one can show that the converse is false. Namely, there exist non-solvable groups which are not uniformly sense. It's not so easy to come up with such a counterexample, but in the full version of the paper, which is available on the archive, you can find such a counterexample. Now, our first main result about uniformly sensed groups is that for every uniformly sensed group, the word problem is hard for the circuit complexity class NC1. And the proof of this result is basically an extension of Barrington's argument. So I won't go into the details. Let me give you some examples of uniformly sensed groups. So first of all, every finite non-solvable group is uniformly sensed. And the proof of this fact is basically Barrington's argument from his 86 paper. Moreover, every free non-abelian group So every free group of rank at least 2 is also uniformly sense. And the proof of this fact, or the proof basically goes back to the PhD thesis of Dave Robinson from 1903, where he proved that the word problem for a free non-abelian group is NC1-hard. Now there are some other examples of interesting infinite groups which are uniformly sense. So for instance, Thompson's group F. So this is a group which appears which appears as a counterexample for many conjectures in group theory. It's a finitely presented group, so these are the two relators or the two defining identities here. And the exact definition is not really important here. It's not needed for this talk. Let me just mention that the Thompson's group F can be also defined in several other ways. It can be defined via certain tree diagrams or also as homomorphisms of the unit interval. Another interesting class of uniformly sense groups are weakly branched self-similar groups. Again, I won't define this formally. It's a very important class in group theory, and some famous examples or some very famous groups are in this class. For instance, the so-called Grigorchuk group, which I will define on the next slide, the so-called Computational groups, and also the so-called Hanoi Tower groups. Okay, so let me give you, as promised, let me give you the definition of the Grigorchuk group. And the Grigorchuk group is defined by a deterministic automaton with output. So that's the automaton which defines the Grigorchuk group. Well, in which way? So first of all, note there are 5 states, and along every edge you read a symbol and you output a symbol. So for instance, if you are in state B and you read the letter 0, you produce a 0, so you copy the 0 and you go into state A. If you then read a 0, you produce a 1 and go to this identity state here. In the identity state, you just copy the input. Now, if you start at any state, for instance, state D, then you get a mapping from binary strings into binary strings. You read a string and at the same time you produce an output string. And it's of course length preserving. The input string and the output string have the same length. Now this mapping from binary strings into binary strings can be easily shown to be a permutation. So in other words, for every state Q of our automaton, we get a permutation, I call it rho sub Q, from binary strings to binary strings. It's a permutation, a length preserving permutation. And again, so for instance, for Q equal A, the permutation is obtained by starting in state A and then reading the input string and producing the output string at the same time. Now the Grigorchuk group is the group of all permutations on 0-1 strings that are generated by these 4 permutations, row A, row B, row C, row D. So the 4 permutations that corresponds to these states. For the state it, well, we don't need the corresponding permutation. It's the identity permutation. Yeah. Okay, so this is the Grigorchuk group, and it's very interesting from a group theoretic perspective. It has very unusual properties. For instance, it was the first example of a group with intermediate growth. So the growth of a group is the number of group elements that you can represent by a word with at most length n. And for most groups, this growth is either polynomial or exponential. For the Grigorchuk group, the growth is actually 2 to the square root of n. So it's intermediate. It's between polynomial and exponential, proper exponential. It has many other unusual properties. So for instance, every element has finite order, which is a power of 2. And there are many other interesting properties. I won't go into the details. Now let me come to another application of uniformly sensed groups. And this application concerns finitely generated linear groups. I already mentioned this beautiful result of Lipton and Salkstein saying that for every finitely generated group, the word problem belongs to log space, to deterministic log space. Now, as a corollary of our results for uniformly sensed groups, we could show that for every group G, for every finitely generated linear group G, the word problem for G is in TC0 or it's in C1-hard. So there is a dichotomy for the word problem of finitely generated linear groups. Of course, it could be possible that TC0 and NC1 are equal. We don't know that. Let me give you or show you some ingredients for the proof. The main group theoretic result that we use for this theorem is the so-called Titz alternative, which says that for every finitely generated linear group, either contains a free subgroup of rank 2 or has a solvable subgroup of finite index. Okay, that's what we use. And then, first notice that if you are in the first case, so if you have a finitely generated linear group which contains a free subgroup of rank 2, then since the word problem for a free group of rank 2 is NC1-hard, it's a uniformly sensed group, the same holds for your finitely generated linear group. So in that case, the word problem is NC1-hard if your group contains a free group of rank 2. So that's the easy case. The other case is that your group has a solvable subgroup of finite index. Every subgroup of a linear group is again linear. So in that case, we have a solvable linear subgroup of finite index. Then we can use a result of König and myself, according to which the word problem for a solvable linear group is in TC0. And the final step is to use this simple fact, namely, if you have a quotient group of a uniformly sensed group is again uniformly sensed. Taken together, all these three facts imply this dichotomy theorem for finitely generated linear groups. Come to the second part of this talk, which is about circuit evaluation problems for groups. So let us start again with a finitely generated group G together with a finite generating set sigma for the group. Then we consider circuits with the following properties. So every input gate of the circuit is labeled with a generator A from our generating set sigma. Moreover, every inner gate of the circuit has a left and a right input gate. And if you evaluate the circuit, then, we first evaluate the left input gate, then the right input gate. We get two group elements from G. We take the product of these two elements in G, and that's the value of our inner gate. Moreover, there is a distinguished output gate in the circuit. So such a circuit can be evaluated in the group G in the natural way. Now the circuit evaluation problem for G is defined as follows. The input is a circuit as described above, and the question is whether the output gate of the circuit evaluates to the group identity 1. On this slide, I've collected some complexity result for circuit evaluation problems. So first of all, it's easy to see that for a finite group, the circuit evaluation problem can be solved in polynomial time. Moreover, if we have a finite solvable group, then the circuit evaluation problem belongs to the complexity class det, which is a subset of NC2, and it's the set of all problems that are AC0 reducible to the computation of the determinant of an integer matrix. On the other hand, for finite non-solvable groups, the circuit evaluation problem is P-complete. And this can be shown again by an application of Barrington's commutator technique. For finitely generated but possibly infinite nilpotent groups, the circuit evaluation problem is also in the class det. So there is an efficient parallel algorithm. And in fact, finitely generated nilpotent groups are the largest class of infinite groups for which we are aware of an efficient parallel algorithm for circuit evaluation. For hyperbolic groups, the circuit evaluation problem is still possible in polynomial time. This is a recent result by Holt, Sol-Schleimer, and myself. Moreover, it's P-complete as soon as the hyperbolic group contains a copy of F2, the free group of rank 2. For finitely generated linear groups, so for finitely generated matrix groups over some field, the circuit evaluation problem belongs to the class CoRP, the complement of randomized polynomial time. And this result is shown by a reduction to the famous polynomial identity testing problem. So the problem where a circuit over a polynomial ring evaluates to the zero polynomial. For this particular linear group, SL3 set, so the set of all 3 cross 3 matrices over the integers with determinant 1, the circuit evaluation problem is actually equivalent with respect to log space reductions to polynomial identity testing. You might ask why circuit evaluation for groups is an interesting problem. Well, first, I think it's a very natural problem if you are interested in groups and complexity. We have seen some relationship to polynomial identity testing, whose complexity status is an outstanding open problem in algebraic complexity theory. But the circuit evaluation problem for groups is also interesting if you just want to solve word problems. For instance, it's easy to see that the word problem for the automorphism group of a group G can be reduced to circuit evaluation for the group G. And in this way, the first polynomial time algorithm for the word problem of the automorphism group of a free group was found. So for a free group, the circuit evaluation problem can be solved in polynomial time. It's a hyperbolic group. Let me also mention that in some papers, the circuit evaluation problem for a group is also called the compressed word problem. But here I prefer the name circuit evaluation problem. Now in this talk, I'm mainly interested in groups where the circuit evaluation problems is computationally difficult. And for this, the wreath product construction turns out to be useful. So take two groups, G and H, then the wreath product of G and H is a new group which is defined as follows. Elements of the wreath product are pairs FH, where the second component H is an element from the group capital H. The first component F is a mapping from H to G which has finite support, which means only finitely many elements of H are mapped to a non-identity element of G, or in other words, this pre-image here is finite. Multiplication in the wreath product is defined as follows. So take two elements, two pairs in the wreath product. Then their product is defined as follows. In the second component, so in the capital H component, we just take the product of the two elements in the group H. In the first component, we have two mappings, F1 and F2 here. And the most natural thing maybe would be, or the simplest thing would be to take the pointwise product of F1 and F2. But here we do something slightly more complicated. We take the mapping F2 and we shift it basically by H1. And then we take the pointwise product. So more formally, the mapping F, which is the mapping in the result, in the product, is defined as follows. F applied to an element H from the group capital H is F1 of H times F2, and then H shifted by H1, or more formally, the inverse of H1 multiplied with H. So this construction gives you again a group, the wreath product, and sometimes the wreath product I defined here is also called the restricted wreath product, where restricted refers to the fact that I only consider here mappings of finite support. There is also the unrestricted wreath product where I do not have this assumption. For finite groups, there's of course no difference, but here G and H can be infinite. Now, what can be said about the complexity of circuit evaluation in wreath products? The following result was shown by Daniel König and myself. So take a finitely generated group G. If G is non-abelian, then the circuit evaluation problem for the wreath product of G and Z, the group of integers, is co-NP-hard. So we have some hardness here. On the other hand, if the group G is abelian, Then the circuit evaluation problem for the group G with Z is in co-RP, and this is again shown by a reduction to polynomial identity testing. Now the first main result about circuit evaluation problems in our paper is a more precise complexity statement for Reith products. For this, let G be again a finitely generated group, and let sigma be a generating set. We need one additional assumption for G, namely that G has a trivial center, which means that the group identity 1 is the only element of G which commutes with all elements from G. Then the circuit evaluation problem for the Reith product of G and a group of integers is complete for this, well, complicated looking complexity class. So how is this class here defined? First of all, here we have a language, which is basically the word problem for G, the set of all words over the generators, such that W is equal to the group identity in G. To this language, we apply this leaf operator. So it's a leaf language construction. Maybe you have seen this before, but I want to define it for those who haven't seen this before. So let's define it in a general way. Take any language L over an alphabet sigma. Then leaf of L is a new complexity class, and it consists of all languages K that can be obtained as follows. First of all, there has to exist a non-deterministic polynomial time Turing machine M, with the additional property that when M terminates along any computation path, it prints a letter from the alphabet sigma. Then an input word X for the machine belongs to K if and only if the so-called leaf string produced by the Turing machine M on input X belongs to the language L. And how do we define this leaf string here? Well, what you do is you take the computation tree of M on input X, and then you list the leaves of these trees, and remember, in every leaf of this tree, the machine prints a symbol from sigma, and you list these symbols from sigma from left to right, and that's the leaf string. So this is a rather classical construction in complexity theory. For instance, the classical class NP can be obtained by taking, for this inner language here, or for this language L here, the set of all words over the alphabet 0, 1 that contain at least one symbol. Here is another example, which can be found in the paper by Hertrampf, Lautemann, Schwentig, Vollmer, and Wagner from '93. And for this, you take a finite non-solvable group G. And here you consider the set of all words over the group G itself. So basically, I consider here G as a generating set for the group G itself. So I take all words over G that evaluate to 1 to the group identity in G. And if you apply the leaf construction to this language, you exactly obtain PSPACE. This is a result from this paper here. And this is again based on Barrington's commutator technique. In this result here, I forgot to say that there is also this OR quantifier here, and this is the same quantifier that, for instance, makes, if you apply it to the class P, you get co-NP. So it's a universal quantification about polynomial length witnesses. Okay. Now let's apply this result. Let me go back. So we have this completeness result for G Reith set. Now assume that group G here is a uniformly sense group. Then what we can show is that this leaf language class here is PSPACE. And this is well shown by an extension of the arguments from this paper by Hertrampf et al. So we get here PSPACE, and then we apply the OR quantifier to PSPACE, which doesn't change anything. You still get PSPACE. So in other words, what we obtain is that for every uniformly sense group G, the circuit evaluation problem for G Reith set is PSPACE-hard. And this has again another application, namely we can prove that the circuit evaluation problem for the following groups is PSPACE-complete. First of all, Reith products G Reith set where G is either finite non-solvable or free of rank at least 2. Well, this is simply true because G is uniformly sense in that case. Another nice application is Thompson's group F, which is also uniformly sense, and it has the additional property that F with Z can be embedded into F. And the result, PSPACE completeness of the circuit evaluation problem, also holds for the Grigorchuk group and the Computational groups. For those groups, you have a similar self-embedding property as for Thompson's group, but their set is replaced by a large cyclic groups, which is still enough for the proof. So let me conclude with some open problems. First of all, is the word problem NC-hard for every finitely generated non-solvable group? This is still open. Here are some concrete word problems which are open. For the Grigorchuk group G, the word problem is NC1-hard, that's what we showed. And you can also show that it is in log space. What is the exact complexity? And the same problem is also open for Thompson's group F. There, the word problem is again NC1-hard. In that case, we can only show that the word problem for Thompson's group F is in log DCFL. What is the exact complexity? Thank you very much for your attention.